Hello everyone, welcome to this video. My name is Sentinel-5. I'm a Google Earth Engine expert. In this tutorial, I'm gonna show you how to monitor volcano activity using sulfur dioxide data in the Google Earth Engine platform. So, in the first step, you need to find an active volcano mountain. For example, in the Russia eastern part, as you can see here, I found a couple of volcanoes here. If you zoom in, turn it to the satellite, you will find a couple of volcanoes here, that some of them are active. At least I know that there are some activities in this region. So now I'm gonna select the top of the volcano as a region of interest. Using drawing tools available here, you can mark your point. There it is. In the next step, I'm going to show you how to find sulfur dioxide data in the Earth Engine platform. Just go to the search places and dataset and type about sulfur. As you can see, Sentinel-5 dataset near real time is available. Sulfur dioxide. Import it as an image collection. Then make a new variable as Sentinel-5 equals to assign image collection to the variable Sentinel-5. Define a filter date to limit your data to a specific range of the dates or for a specific year. So, two variables needed for two arguments. One argument start and another one end date. So, make two variables. First, time start. Earth engine.date converts your string to the date format. The string value is 2023 and time end equals to same format for the end date. Instead of these two arguments, time start and time end, we will have time start and time end, just like that. Couple of bands available in the image collection. So you need to go to the data description first and then bands. Here there is a resolution. It's around 1 kilometer, 1000 meter. So, and the target band is SO2 column number density. Copy its name and then back to the code. To select the target band, select is a function allows you to select each one of the bands you desire. This is the target band name, and then I'm gonna make a print to see that how many Sentinel-5 data is available for this period of time. Sentinel-5.size. .size allows you to calculate the number of images available under Sentinel-5 variable. Click on Run. After a few moments, in the right panel, you can see the number of images available for this region. 45,000 images available for this region, meaning that the temporal resolution is actually not limited to the daily frequency. It is higher than the daily frequency, maybe hourly or 3 hours or something like that. In this case, we will have a lot of challenge for the process of 45,000 data on the Earth Engine platform. I'm suggesting you to convert this data to the daily format. For example, for a 1 year, 365 images expected. And now I can make daily average from these data. It is very simple technique. In the first step, make a list. Here Earth engine list.sequence. Now I'm gonna have a list of numbers. I'm gonna have a list that in which I'm gonna fill it by different images for each days. And this list, the length of the list actually explained by the number of the day and days difference between time end and time start. So the time difference is like that. Time difference equals to from time end dot difference. Difference allows you to calculate the difference between two times. Here is time end and time start. Here we have time start, and the next is about the unit. Based on what kind of unit you want to calculate the differences. The days, the months, the weeks, it is important. For example, here, I'm gonna get the difference based on the number of the days. Let's make a print, time difference. In the right panel, you can see the temporal difference is 365 days from 23 to 24. So now we want to make a list based on temporal difference or based on time difference. So couple of arguments you should consider for the list of sequence. A start value should be equal to 0, and the end it will be set based on the time difference. But as you know, when the list is starting from 0 and ends to 365, in that case, we will have 366 rows that could make a problem during the process. That's why we need subtract it from 1 to have access to 365 rows because it's starting from 0. And the step for each value or each day will be 1 because we want to have the daily data. Skip the count now. Print the list. In the right panel, you will have a list with 365 elements starting from 0 and ends to 364. There it is. The list is ready. The list is going to be a framework that you will fill it with different dates and finally different images. So, in the next step, I'm gonna have a start date for each row. Here, we want to make a loop using .map, and then to fill it with the date information, a function needed. Each input day or day number, consider it as a day, and now the function returning the time start from time start .advance from time start already defined as 2023. We want to go forward using advance based on a couple of considerations. The first is the delta. The delta will be defined based on a day, based on a value number we already have in the list. The unit will be days, and I skip the time zone. So, remember to save your code and run it again. Again, you will have a list with 365 elements, but this time, as you can see, the list filled by start dates and starting from January 23 and ends to December 23. There it is. The start dates are ready, and now we want to define the end dates with 1 day interval. It is very simple technique. Just make a little space for the rest of the code. A new variable as daily created. Daily equals to So Earth engine dot image collection. I'm gonna have an image collection because the input is a list and I need to convert it to the image collection because I'm gonna do some sort of image processing in this regard. For each day, I'm gonna have daily data. So bring the list inside the image collection and make a loop and do your process based on a function. The function including the date information. So here in the body of your function, you will have the start date. Start date equals to Earth engine.date. This is the that date that we already have in the list. So, but what about the end date? End date equals to end date calculated or started from the start date dot advance going forward based on a delta. This time delta is 1 because we want to have daily data. From the start date, we want to go forward based on 1 day interval. This is again the unit is days, and skip the time zones. The start date and end date created. Next, we want to filter our data based on start date and end date to capture all images available every 24 hours. So here, img equals to all images already stored under Sentinel-5 variable. That filter date. Now we can filter it based on every day, time start or time end. Here it is. The argument start this time equals to start date and equals to end date. Then I'm gonna get average for whole of images available for every day. There it is. Finally, the function returning the img with new system time start and new system time end. That set allows you to make a new property for the time start and time end. System time start equals to a start date with millisecond format. As you know, the Earth engine, for the time series analysis, the Earth engine uses the millisecond format, not the normal format for the dates. So that's why we need to convert it to the millisecond. That's it again. System time end date with millisecond format. Daily data created or daily average is created. If you make a print in the right panel, you will have a new image collection with 365 elements. If you go here, you will see for each day you have a one average image for sulfur dioxide. So now the daily data is ready. The simplest way is actually make a chart showing the sulfur variations or sulfur emissions from the top of the volcano. It is very simple part. So make a print, user interface, chart, image.series. Instead of image collection, you must have the daily data. The region of interest is geometry. The reducer, as it is a point, the reducer must be first. Earth engine.reducer.first, meaning the first value captured by the point will be displayed in the chart. The scale equals to 1000 meter because the spatial resolution is 1 kilometer. X property explains the temporal variation. Its information already stored under system time start property. So, as to get a better understanding, it would be better to set the chart type as a column format. Column chart. Run the code. In the right panel, a new chart is generated. As you can see, the sulfur dioxide value is very low. But if you look at the chart actually with more detail in the larger scale, then you can see that although the sulfur dioxide has discrete value for these days or for 23, but we can see that in some of the dates, such as April 23 and March 23, and also the other dates such as May 23 and June 23, we had some sort of activities in the volcano, because at the top of the volcano we can see clear increase in the emission of sulfur dioxide. This is very helpful thing to understand when the volcano had activity, because when the activity increases in the volcano, the value or the number of sulfur dioxide will be increased because its emission increased in the top of the volcano. So now in the next step, I'm gonna highlight the changes with meaningful values. For example, I'm gonna get the anomaly of the sulfur dioxide for this period of time, and then detect those of the dates in which the value of sulfur dioxide is above the mean average. But before then, let me to make a visual image or visual interpretation from this region to show you how the pixel values looks like for this region. So, suggesting you to make a new geometry and then go to the satellite view and draw a bigger region that include all the volcanoes in this area. So then use the map.add layer here, and as you can see, map.add layer, we can visualize our daily data. For example, I'm gonna visualize the biggest activity or the highest activity that is for April 11, 2023. So that filter Earth engine, that filter, that calendar range. So I'm gonna get the images for the April starting and ending months equals to the April, or the simpler way is make a new filter date. For example, here, make a new filter date 2023 April. I'm gonna have image from April 10 to April, for example, 12, 2023 April 12. Or if you want to see the exact the image for April 11, only you want to have this single data. You must set the start date to April 11. So then I'm gonna have this single image. Use dot first. I'm selecting and then clipping based on the geometry number 2. Leave the visualization parameters empty, and the layer name is, for example, eruption, and use the false at the end. Run the code and turn geometries off. Go to the region. Eruption image is ready. So as you can see, the pixels only recorded values over the top of the volcanoes. As you can see, these are completely covers the above the volcanoes that highlights the gases coming out from the top. You can increase the contrast to get a better understanding about the values in this region. Lighter pixels showing higher eruption, for example, the higher gases detected for this region, but we have lower gases in this region. Even you can get the maximum gases or sulfur dioxide for each day in the aggregation process. Run a code again, and here the eruption image is ready. Increase the contrast and click on apply. Here it is. And as you can see, we had higher emission in the southern parts, that all of the values and all of the actually emissions recorded at the top of the volcanoes or near to the top of the volcanoes. That is very, very helpful and interesting results that help us to get a better understanding about activities over the volcanoes. So, if you want to get export or have this layer, to open it up into desktop software, I'm gonna suggest you to use export.image to drive. This is a popular function, allows you to export from Earth Engine to Google Drive. So, a couple of arguments should be considered in exporting process. The image equals to daily one, or you can completely copy and paste this part. Here, daily the filter date for the target date selected, the first image selected again, and then description refers to the output file name. Here it is, for example, eruption test scale equals to 1000, region of interest geometry number 2, maximum pixel no need because it's coarse spatial resolution and the region of interest is very small. The next parameter is necessary. The next necessary parameter is CRC coordinate system, EPSG 4326. This is WGS84 code that you can use it for all around the world. So description, scale, region, CRS, and also the target folder you want to save data in. So for example, I'm gonna make a test folder and save the test imaging. So after all parameters settled, click on Run. In the right panel, after a few moments, you will have a new image. Click on Run and again on Run. The process of saving is started. Once the tab color turned to the blue, meaning that the file is completely saved, and then you can pick it up from the Google Drive. So, and now you know that how to deal with the Sentinel-5 data and also volcano eruption in the Google Earth Engine platform. In the next step, I'm going to show you a technique regarding to the anomaly detection. Now I'm going to show you how you can detect actually some sort of noticeable activities in the volcanoes that cause sulfur dioxide emission in the region of interest. So here we want to have, instead of checking the calendar or the chart to see when sulfur dioxide comes up or when comes down, now I'm going to show you an automatic way that helps you to extract all the dates in which volcano had activity. So it is very helpful technique thanks to anomaly detection method. Now I can show you how to deal with. First of all, make a daily average. So because I'm gonna see that when the sulfur dioxide comes upper than daily average and when coming down or lower than the daily average. It is very important. That's why in the first step, we need to have the daily average for each pixels. So in order, if you want to have a realistic average without extreme value impact, should be better to use the median. Get the daily data and then calculate the median for each pixel separately. So next, I'm gonna show you how to calculate the differences between daily data and also the average. Here, the anomaly equals to, so get the daily data, bring it into a loop structure, and apply the equation using the function. So the function returning a subtraction between each sulfur image from daily average or daily median with the properties of input images, that property names. Let's make a new variable for anomaly equals to this equation, and then I'm gonna have the anomaly value as a property next to the image, because it is very helpful technique to make a query based on the properties in the next step. So another variable is a statistic equals to from anomaly image dot reduce region. I'm gonna calculate the anomaly value for each date and have it as a separate properties. So couple of arguments we have. The first is Earth engine dot reducer dot first, because the region of interest is a point. The geometry is for visualization, but the target point is actually recently marked, and that's why we need the first instead of the average. Geometry equals to that point, or geometry and scale equals to 1000 meter. There it is. Now we have the anomaly value for the point. If you want to have it as a number, that values that get first item should be used. To ensure it is a number, Earth engine number uses. So finally, the anomaly image returns by the function with the existing properties. Then you can add the new property that is stats. Its name could be stats, or its name could be anomaly equals to stats. Print anomaly image collection now. Again, we will have a new image collection with 365 elements. It's a little bit time consuming, a little bit longer compared to the previous process. So, as you can see, the image is ready. For each date, you will have a new anomaly map that shows the differences between each date or each day and long-term average. And in the properties, you must have a new property as anomaly, but unfortunately it is missed. To ensure if a stats or a statistical parameters calculated or not, I'm suggesting you here get aggregate array. Aggregate array based on anomaly stats gives us a better understanding whether a stat is calculated or not. Right click, run the code, and here there is a list. It shows that for 19 dates the stat is calculated, and you can see that we have the value for some of the dates. But here also should be first. Because of the low values or lack of values in the other dates, you can see that the statistic only, or the anomaly statistic only calculated for those of the dates that we had the values. It is 19 dates, and here it is. You can see the positive and negative values. As you can see here, the positive value shows sulfur emission was higher than the normal average. That's meaning that maybe in these dates we had some sort of activities on the top of the volcanoes. So the next step, I can make a new variable for activity or activity dates even, or just activity first, because I'm gonna filter the data based on positive anomalies. Variable activity equals to get the anomaly data and then make a greater than filter. First engine.filter.gt, greater than. I'm gonna filter data based on anomaly statistic. Those one, actually their anomaly is greater than 0. So print activity. Activity again, and run the code. Now we have an image collection including all sulfur dioxide images relevant or belongs to the volcano eruption or volcano activities. Maybe it wasn't an eruption, just simple activity that caused sulfur dioxide gases comes out from the volcano. So here, if you want to have all image with their dates in a stack layer, it is very simple. Now we can make a loop here, a function for each image. So to extract the data of each image, or we can do it before. For example, remove the extra code from here and go to the previous variable. It was anomaly. Here we can add a new, variable or properties that explain the date of each image with a normal format instead of millisecond format. So now a new variable as date. From each input image, I'm getting its date and then convert it to the normal format according to year, month, and day. So next to the statistic, make a new property as date here, and then we will have a date. Or you can change the system index to the date format, but it must be a string, just like that. So print activity, just like that, and run the code. Now we will have the same image collection, just with a new property that it is the date. As you can see, unfortunately it is missed again. That's because we already had a system index, and but it doesn't change or doesn't update. We can make a new one as date. Run a code again. In the right panel, here it is. We have 9 images with a new properties for the date. If you want to see the dates in which volcano actually gases comes out, you can use the aggregate array. For example, from activity variable, I'm gonna sort or I'm gonna list all the dates in which the anomaly of gases was higher than the normal average. So that array based on the date. In the right panel, there is a list that shows the dates in which anomaly was positive. Here it is. These are the dates with positive anomalies. So, and if you want to have them as a layer stack for the raster layer, now we can have a stack variable equals to activity.toBands, just like that, and print it as a stack. In the right panel, you will have one image including 9 bands, each band for a separate date or for a positive date. So if you want to see the date in the name format, or if you want to see the name of the band and also date of each image in the name format, it is very simple technique. Here I can make a loop again for each image, and now the image returns. First, we must make a variable that bring the date, bring it up from the property first, date equals to, from property gets the date first, and then each image should rename based on the date information. So run a code again. .toBands also must be added. Again, we will have a new image including 9 bands, but there is a problem, invalid type. Let me to convert it to the string format and run the code. I hope this works now. Yes, the problem is solved, and as you can see, we have the date of each image in the name, and then you can save this layer using export.image to drive as it is already explained, and using map.add layer you will be able to visualize the results that is already clipped based on the geometry number 2. Leave the visualization empty and the layer name is stack activity, and use the false to avoid automatic visualization. Run a code again, and here you will have a stack layer including all positive anomaly images. So it's a little longer if you want to do visualization. So when you click on each image and increase the contrast, you will be able to see the pattern of gases over the region of interest. These are the dates that some anomaly is detected or positive anomaly is detected. from the satellite data. It would be better to download and bring it into the desktop software to see the variations. As you can see, exactly above the mountain here, some anomalies detected. In some dates, it is lower positive value, or the other dates, a little bigger positive values. I'm waiting to update process and then click on apply to see another image here. I hope you like this tutorial, and I tried to show you how we can use sulfur dioxide data in the Earth Engine platform. And also you can ask your questions on my YouTube channel, and also the code link is available below the video, actually below the video in the description box, and you can compare yours with mine. And also, if the problem still exists, you can reach me out by actually asking questions in the comments. As you can see, for the other dates, other gases also emitted from the other parts, or it is possible to be detected by the satellite for the other regions. But the thing is that you must select the top of the mountain or top of the volcano for your study, because it is exactly matched with the gases coming out from the volcano entrance. So this is for another date that I'm doing the visualization process. Thank you for your attention and have a good time.